to be the host of this week's session. Please join me to welcome Dr. Roberto Perdisci. Dr. Perdisci is a distinguished professor in computer science at the University of Georgia, where he directs the UGA Institute for Cybersecurity and Privacy. He is also an Adjunct Associate Professor in the Georgia Tech School of Computer Science and a member of Georgia Tech Institute for Information Security and Privacy. His research interests include network and web security, and malware defense, security applications of AI, IoT security, and telephony security. Dr. Perdisci is the recipient of the 2012 NSF Career Award and one of the 2015 UGA Early Career Scholar Award. He has published over 60 peer-reviewed papers, many of which have appeared in the most selective computer security and systems conferences and journals. His research has been sponsored by grants from the NSA, DHS, DARPA, and an industry grant from Intel. His past research on malware download defenses was selected by DHS for the Technology Transition to Practice (TTP) program, and he has been promoted as prestigious industry venues, including the RSA conference. I personally learned a lot from his interesting research. And Dr. Perdisci, welcome again to our weekly seminar, and thanks for accepting our invitation. The floor is yours.
Thank you. Thank you very much, Amin, for the introduction and for the invitation to give this talk. So, as Amin mentioned, I do research on a number of topics, but today we're going to focus on web attack reconstruction, which is actually one of my favorite recent research topics that I've been spending quite a bit of time on. So just as an introduction to motivate the talk, as you probably know, many security incidents nowadays originate from the web. Malware downloads, or phishing attacks, or spam of different kinds, and so on and so forth. They essentially come from the browser, through the browser, let's say. So let me give you a quick example, classic example of a malware download, how it could happen. So say that you're looking to, watch a video, like a recent movie that you want to stream. Let's say you don't want to necessarily pay for it, which is not uncommon, especially among young people. And you find a website that claims that you can stream the video for free. And if you click on that play button that you saw, you might see something like this that says that your Flash player or your codec, some video codec, for example, needs to be updated for the website to stream the video. And unfortunately, although the page is nice enough to also provide you with all the information about how exactly you should go about installing the software, you might find that the software is malicious and your machine is going to be compromised. So obviously, this is just an example, but it's something that actually occurs very frequently, maybe more frequently than you could imagine. And so web attacks, of course, are important, especially in enterprise environments. An attack of this kind could really bring to nefarious consequences, whereby the malware could spread through the enterprise network, potentially infect, POS, the point of service devices, steal credit card information, and so on and so forth, and create a lot of financial damage, of course. And in other cases, could be used for as spyware, let's say, for espionage and all sorts of other malicious purposes. So we really need to care about these type of attacks. And another thing to consider is that there are a lot of examples of attacks of this kind, well, not necessarily originating from the web, but in general, in which these types of security incidents are discovered many weeks or even months after the original attack took place. And often, at least in the case of enterprise environments, what happens is that when such breaches are discovered, a forensic investigator is typically brought in to essentially find the root causes. What caused this data breach, say, and the monetary loss. And understanding how web-driven attacks unfold, if that was the origin of the attack, is very important. Obviously, it would allow us to potentially discover unknown vulnerabilities, learn how, say, maybe social engineering an attack, if there was the entry point, was tricked, say, one of our users to click on a link that shouldn't have been clicked, and in general, assess the damage. The problem, though, is, and the question, really the research question is it possible to reconstruct exactly where the attack came from, especially, which is the focus of this talk, when the attack came through the browser, right? For example, following the path that or the example that I discussed previously. So to answer this question, me and my students and collaborators, we went through quite a long process, and we were able to publish several papers. But I wanted to kind of give you an idea of how did we get to, first of all, asking that research question, and how did we progress to the subject of the talk today. So really, the research question came about when I was still at Georgia Tech as a postdoc student as well previously, working on detecting malware, mostly by performing network traffic analysis. So in an, say, enterprise or ISP network environment. And we built several systems for that purpose, meaning to detect malware infections. But we were always in the dark in terms of, okay, we can detect the fact that a machine has been infected with a piece of malware. But the question is, where did the malware come from? We have no idea how it got there. And so that's where we started thinking about this problem more. And because we were working on the network side, what I asked my students to do was, well, let's look at the network side in terms of, okay, can we actually reconstruct where the malware came from? And so we had a number of papers on that, trying to use network traffic essentially for analysis and replay even to try to figure out exactly, okay, can we trace back the origin of this infection? And unfortunately, as you can imagine, even back then, before most of the web traffic was encrypted, things are quite difficult at the network level. If you're just looking at network traffic, you typically have little information to work with. Even if you do deep packet inspection and so on, there is a huge semantic gap between what happens inside the browser and how those events are reflected into the network traffic. And so it was, although we had some successes, and that's why we were able to publish pretty good papers in top conferences, we always had this gap that bothered us, that bugged me in a way. And so we looked at the problem, started looking at the problem in a different way, which is from the browser side. And that's where we started to really work on browser instrumentation to try to really figure out how attacks of the sort that I showed you earlier actually work inside the browser. So that's the topic of today. I will not be able, of course, to talk about all these three works in detail, and there are also follow-up works beyond these ones that I will not be able to describe in detail, but I will talk about a couple of them, especially one in more details. All right, so if we look at performing attack reconstruction from inside the browser, well, what are the challenges? Well, the first challenge is that browsers are extremely complex pieces of code. They are essentially operating system for the web, right? I mean, if you think about it, whenever you visit a website, there is a log going on there. You're essentially running a web application inside your browser. and multiple web applications at the same time. The browser performs site isolation, to sandboxing of web origins, and so on and so forth for security reasons. And so it's really as complex as an operating system. Millions of lines of code, essentially. And the problem is that also we cannot really use what the existing operating systems offer us in terms of audit logs, for example, audit logging modules, because they really don't give us information about what happened inside the browser. And so when we are trying to reconstruct a web attack, we really want to trace it back to exactly what happened inside the browser. For example, did the user click on a link because of a social engineering attack? And that's very difficult to reconstruct if we only look at the OS level logs. If we look at the existing logs from the browser, they are really sparse. Typically, you have to grab the cache or navigation history. You get URLs potentially, but not much more than that. And so it's really difficult to figure out what happened. And like I said earlier, if you just look at the network traces, there is a huge semantic gap that you cannot fill. And so really our goal was to say, okay, fine. So there is no audit logging system for the browser. Can we build one? And what does that mean? Like, what are the trade-offs? So we started with a work that we call Web Capsule. And then we proceeded with two more that I will be focusing on in the talk. So, but first, the requirements. What if we want to build an audit logging system for a new operating system, essentially a web operating system? What are the requirements? So first of all, as for the other operating systems, it has to be always on, right? I mean, attacks are unpredictable, ephemeral. You don't know when they happen. So the logging has to be on. To give us a chance to later, look at the logs to try to reconstruct the attack. Obviously, the logging has to be efficient. We don't want to impact browser usability in terms of lagging, in terms of response to clicks and so on and so forth, because obviously nobody would use it. And forensic rigor in terms of we want to make sure that when we record the traces of an attack in the logs, that the attacker cannot do anything to kind of like hide their traces. And maybe it will be a bit more clear what I mean with this later during the presentation. We also want no functional interference. We don't want to alter in any way whatsoever the way the browser works. There's a lot of work that goes inside the browser into the browser code to provide security, privacy, efficiency, and so on. We really don't want to interfere with any of that. We don't want to risk to break anything. So we just want to tap into the browser functionalities that exist without changing its architecture. Also, the login has to be completely transparent to the user. No actions need to be coming from the user to enable the login, as I said earlier, with the always on requirement. And also, of course, we want limited storage, right? Because if the logs take such a large amount of space that we cannot store more than, say, a few hours of activities, then they're basically useless. Because like I said, some attacks or data breaches are discovered much later than the actual original root cause attack. And the assumption I'll be making is, of course, that the browser itself is not compromised. And that also the security and privacy of the logs themselves can be protected via existing solutions. I will not go into the details of this, but if you have any questions, I'll be happy to talk about this after the talk. So our first attempt to solve this problem, which I will anticipate that it's sort of failed, and I will explain why. So we started with this building this system, which we call Web Capsule, which is a whole browser record and replace system. Essentially, the idea at a high level was to say, hey, the browser it receives inputs and produces outputs. Well, what if we record all these inputs that are received from the users, from the web, from the interaction with the underlying operating system? Well, can we record this in an efficient way And later on, we can just re-input them into the browser somehow to replay exactly what happened before. And we did have some success, and I encourage you to visit our website there with some, where we have some demos essentially of how Web Capsule actually worked. And of course, we had a paper in CCS, which is great. But I think that the truth is that we started with a goal that was a bit too ambitious. Doing whole browser record and replay is extremely, extremely hard. There's way too much going on into such a basically operating system to be able to record everything and replaying deterministically, which was the main limitation. And also large storage requirements were certainly another limitation as well. So I will not go into the details of how Web Capsule worked because I don't have time, but I encourage you to, of course, look at the paper if you're interested. So the second step was to say, okay, well, Web Capsule worked, but it didn't. It worked, it was great to some extent, but then we wanted deterministic replay. We didn't get there. And so the question was, all right, what about if we focus on recording? After all, we are trying to build an audit login system. We really need to focus on recording the logs efficiently and be able to later reconstruct the attack, but maybe we don't need to replay to do that. So that was the motivation for looking at Chrome PIC, which is the second project we worked on. And here the idea was fairly simple, which was we were focusing on social engineering attacks, reconstruction of social engineering attacks, which have a very prominent visual component, right? The user needs to actually look at the social engineering attack typically, and then be tricked into doing something that shouldn't have been done. And so we thought, okay, so what if we wanted to record everything that the user sees and does? We created this concept of recording a web shot, which is essentially a combination of a screenshot plus a DOM snapshot. The DOM is the representation of a web page inside the browser. So a deep DOM snapshot that really takes not just the shallow DOM representation, but also the embedded objects and records everything essentially efficiently from that front. Also, we wanted to do this synchronously with every user action, a click or a key press, and so on and so forth, because we wanted to make sure to have that forensic rigor that I mentioned earlier, which is that we really don't want the JavaScript engine to take over for whatever reason and execute potentially malicious code before we actually record the logs related to a certain event that happened in the browser. So that's what synchronous really means. So we thought, well, maybe we can do this with an extension. And the answer was, well, no, we can't. And the reason is that, first of all, simply the extension API is not built to support such type of logging. The events, the screenshots cannot be taken synchronously. The snapshots of the DOM are extremely inefficient. And so it really didn't work out. So the alternative was to actually go inside the browser, and we took Chromium, which is essentially the open source version of Chrome, to see, okay, can we do this if we just put our hands inside the browser and start instrumenting it? So just to give you a little bit of background, which may allow you to understand a little bit better how Chrome PIC, our project, works. So Chromium is a highly multi-process and multi-threaded application. So first of all, there is a browser process. There is the main process that handles all the user inputs and so on and so forth. And then there are render processes, which essentially run the web applications that you visit. The websites essentially that you visit are web applications. So there is a rendering engine, which is Blink, and there is a JavaScript engine, which is V8. Blink runs the HTML, CSS code, essentially, markups, and renders them. And V8 is the engine that takes the JavaScript code and executes it. And Blink and V8 interact very closely through an interface that is called the bindings. So in any case, so that's more or less how at a high level Chromium works. And why is this important? Well, because to achieve the goal of ChromePick, we actually figured out that we needed to instrument pretty much both sides, I guess, of Chrome, meaning the browser process and the render processes as well. So things look a little bit like this. So that whenever a user input arrives, there is a browser process thread, the UI thread, that will process that input, send it to the browser IO thread, and then through an IPC message, these input will be communicated to the correct render thread. So if you had a render thread that was rendering google.com, then that, and the user clicked on something on that page, the browser process will basically route that message to the correct render process. Okay, so the good thing is that, this is a nice architecture, but it comes with a lot of complications. But the good thing is that there is already code to do sort of what we wanted to do in Chrome, in Chromium. There is code to take screenshots, and there is code to take DOM snapshots, actually deep DOM snapshot, which are called MHTML format snapshots. It's the M stands for multipart, which allows you to take basically a dump of the the HTML of a page, but also the embedded objects as well. The problem is that these functionalities were certainly not devised to or implemented to enable OD logging, with forensic rigor and all of that. And so they are extremely inefficient. And so the question was really, okay, can we reuse this code, but make it synchronous and efficient with what we want to do? Synchronous with the user inputs and efficient, obviously, for obvious reasons. And so our approach was the following. So we wanted to essentially say, okay, so whenever a user input comes in, we want to log this action and take basically like I said, a web shot. So freeze the browser and tell us log exactly how the browser looked like, meaning the page that was rendered visually, and what was the structure of the DOM at the very moment in which the user clicked on that link button or whatever they pressed on the key, and so on and so forth. And now to do that, like I said, whenever an input comes in, the browser sends that input to the right renderer thread. And essentially, we use that as a cue to start our process of taking a dump of the DOM, a deep snapshot, essentially, of the DOM, and also to start the process of taking a screenshot, and then eventually tell the renderer thread that, hey, we finished taking a screenshot, so you can move forward and do whatever you needed to do, which is respond essentially to the user event, typically run JavaScript, navigate to another page, whatever that is. And there is a twist here, which is something that we had to add to the browser, which is the fact that, here on this side, obviously, once we take a DOM snapshot, we want to save that on a log file, like we do here on the browser file thread. But the render thread doesn't have direct access to disk and cannot open a file. Everything is sandboxed for security reasons. And there is fortunately a trick that we found, which is to open a file at the browser process side and pass the file descriptor to the renderer, so that when the file descriptor arrives here, we take a snapshot and we can save it to that file. And the browser thread, the browser process will take care of opening and closing the file whenever it's necessary. All right, so all of these basically would give us the web shot we wanted and synchronous with the user inputs. So now the problem though is, can we do this efficiently? And we put ourselves into a situation in which we wanted to keep an overhead budget of less than 150 milliseconds. So meaning all these process taking the DOM snapshot and the screenshot and sending a message here to the render process to tell it, hey, you can move forward and process the event and do whatever you need to do. All of these needed to happen in under 150 milliseconds. So why 150 milliseconds? There have been studies in HCI that show that if you delay the response to a user input by more than 150 milliseconds, this starts becoming noticeable by the user, and the user gets annoyed. You don't want the lag, obviously, and so we wanted to stay under that budget. All right, I'm not going to go into all the details of this, but just the high level. So how, like I said earlier, we wanted to reuse the browser's code, but twist it a little bit, or tweak it, not twist it, but tweak it so that we could do things efficiently. So this figure just shows the somewhat complicated process used by the browser to actually render, or not to render, but to visualize a page. Let's say after the Blink rendering engine is done with the layout and so on and so forth, there is a process through which the actual image needs to be formed on screen. And so that's what this is essentially showing. And the easy way was to say, okay, we call this function that takes the screenshot, and we wait until the screenshot is done, and then we send a message to the renderer to say, hey, we're done. You can move forward. But this didn't work, and the reason is that this process is extremely inefficient, taking up to 1 second on mobile devices, which obviously is a delay on user input response that is absolutely unaffordable. And so we really had to inspect the code here of all this process, and we figured out that actually we didn't need to wait for the entire set of steps to finish. We could actually take a screenshot much earlier, and which was here after this draw frame function is called. Without going into the details, essentially what happens is that even if the image is not yet visualized on screen, it needs to be cropped and whatever else, we can still take basically a memory copy of the buffer in which the image that is being processed is copied, and just move forward, because at that point there is no chance that the attacker is going to be able to modify that image in any way whatsoever by running, say, JavaScript or to change the page or anything else. And it turns out that these processes, these messages can be linked to the vertical drawing frequency of the monitor of the screen, and so it turns out that it's much more efficient than just waiting for the entire function to complete. So this gave us that efficiency that we wanted. All right, that's for the screenshots. For the DOM snapshots, for the deep DOM snapshot, we also found that using the code that Chrome had originally was impractical, because, well, as you know, a page may be composed of multiple frames, and it turns out that the process that the browser was using is that it would basically ask, if you ask the browser, okay, give me the MHTML version of this page, and dump it, that's the browser is going to send a lot of messages from the browser process to the renderer saying, hey, okay, save frame 1, save frame 2, save frame 3, save frame 4, and so on and so forth. And in between these scheduled tasks that the browser process is sending to the renderer, there could be some JavaScript that could be also malicious, essentially distributed by the attacker, the attack page itself. And the problem is that even if this JavaScript is not malicious, it could start running and delay the process of completing the dump of the page. So basically, the point is that the render is an extremely complicated and kind of a scary place to work in terms of the code itself. And because of how JavaScript is scheduled to be executed, and some long-running JavaScript can stall the browser for a long time. So we certainly didn't want to, we wanted to avoid that for exactly the efficiency reasons that I said earlier. So we had to re-architect that piece of code in Chromium and basically do things synchronously with the inputs, and also do all the dumps of all the DOMs of the frames in a page all at once and essentially freeze the render thread until we are done, and then the input can be processed, and then if there is any JavaScript, it can be executed. And even if that JavaScript is malicious, it doesn't matter anymore because we already dumped all the information we wanted into the audit logs, and there is no chance that the attacker could alter the look or the state of the page before we recorded the event, because we have already done so. All right, so those are quite a lot of details. Hopefully not too much, but I would be happy to go even more into the details if you have specific questions later. Let me give you an example of an attack that can actually be reconstructed real world. Social engineering attack on an Android tablet that we recorded with our logs, and could be visually reconstructed because of the screenshots, and also an analysis of the DOM snapshots can be performed as well. So here, a user is typing Wolf of Wall Street full movie. The user didn't even complete the entire sentence. A suggestion from the search engine provided the title. So the user clicked enter, and that's this space here. Chrompic took a screenshot of this because of the enter action or event, or the key press event, sorry, I should say. And at that point, there was a navigation, and the search results appear. And this is the first portion of the search results. And this is the first, this is a real world example, okay? Nothing is made up here. This is what the user saw. The user saw these as being the first link in the search results, which brings to this fmovies.to whatever streaming video streaming website. Which is amazing that, by the way, that this is the first result in the search. And in any case, what happens is that there is this is the page that actually is rendered initially, but immediately there is basically this page is replaced by this one. So this is what the user saw initially on the browser for a second, and then immediately there was an automated redirection to this page. So this is the actual page that the user saw. Your system is heavily damaged by 4 viruses and so on and so forth. This was done on a Google Pixel C as a device, Android device, and so that's why it's reporting this. Anyway, this is a scary or scareware tactic, right? So the user is just browsing, right? And they see this, oh, Google is telling me that my Android device is infected. So we recorded this, so there is a screenshot of this. There is also a log related to the an alert pop-up alert window that is recorded by Chrompic, which contained this message. What we did not record was this initial page because there was no user interaction with the page whatsoever. There was an automatic immediate redirection from here to here. So now later on, we said, okay, we can slightly modify Chrompic to also take a screenshot of this by looking for the load event when they trigger. We can take a screenshot of the page and so on, but we didn't do it at the time, and so that's why we missed it. In any case, when the user actually clicked on this link, repair fast now, which was actually the only thing that the user could do, because any way you clicked on this page, it would actually bring to the following, which is redirect you to the marketplace or to the Google Play Store, where the user was recommended to install this Go Speed, Clean, Boost Free, whatever application. Now, we couldn't determine if this application itself was malicious once installed, but what we could determine is that the people who were running these social engineering attacks were actually making money out of redirecting people into this installation of these applications. Essentially, we think that the people who developed this Go Speed application would pay the attacker for redirecting users into the Google Play Store and downloading the app. Whether the app is malicious itself, we don't know. We did other experiments with Chrompic to reconstruct other types of attacks like phishing attacks and clickjacking attacks, and showed that that it was effective because of the synchronous web shots that we take and so on and so forth. We could also reconstruct leak-injection attacks. And I'm going fast because of of the time. Again, if you're interested in these things, I'm happy to stick around after the talk as well with extra time if you're interested. Now, in terms of evaluation, we focus on two things. First of all, efficiency, and second thing is storage overhead. So let's talk about storage overhead first. How we determine that? So first of all, we decided to run a user study because we wanted to figure out, okay, so if a real user uses our instrumented browser, how will they perceive it? And so while the users visited the multiple different websites on multiple different devices, we basically stored the Chrome peak logs and measured how much space we needed per user. And it turned out that we really could afford to store a lot of logs, which included the compressed screenshots and images included in the pages, in the DOM, and so on and so forth, which was actually a very good result. In terms of the actual processing overhead, CPU overhead, essentially, we performed this interesting experiment, which is to essentially measure how long does it take for Chrome, or for Chromium, for the browser, to process a mouse click or a key press, and compare that with the time that it takes for Chrome peak to actually take a web shot, screenshots plus the deep down snapshots. And this CDF is basically showing that as a result, in average, essentially, well, if we take the median, for example, the median is showing that it takes more time for a user to click on a mouse button and release it, or a key press and release the key, than it takes for Chrome peak to actually take a web shot and record it. So that's essentially what these curves are saying. This is the time, and this is CDF. So, and this is the 150 milliseconds mark that we set as our own maximum budget. Now, in some rare cases, we would go beyond that, especially this curve right here for taking a web shot on a tablet. But in general, like in the vast majority of cases, we could take our web shot, like I said, before the user even released the mouse click. So basically, the user would perceive zero latency in a way in the response from the browser. All right, so that sounds good, but what are the limitations? Well, the main limitation that we found was that Chrome peak was nice as a project because it really allows you to actually visually reconstruct an attack and exactly know what happened in between user events, what the user clicked on to get infected or to be phished or whatever else. But we didn't have information about what the users were, what the attackers were using to build the page, to build the attack. Most attacks are built through malicious JavaScript code execution, even for, not just for the drive-by downloads and so on, but also for social engineering attacks, phishing, and so on and so forth. There is a lot of obfuscated JavaScript in there that may be running. We didn't have any trace of that. Chrome peak doesn't do that. And so we went ahead to build another system that complements Chrome peak, which we call JS Graph. And essentially, I will not go into the details of all of these because we don't have enough time. But the purpose of JS Graph is to log all details about navigation events, DOM changes, either reflected by or caused by parsing the content of a page or by rendering executing JavaScript, which can, of course, interact with the DOM and change the DOM. And also we wanted to record all dependencies between events and JavaScript callbacks and so on and so forth. And the reason why we wanted to do this is because we really wanted to understand how malicious JavaScript that is used to build, say, a social engineering attack on the web, how does it run? What does it do? And so after logging everything, so we built this auto login system for JavaScript, essentially. We also built a sort of like a forensic analysis tool that would take the logs and create these graphs that would allow you to reconstruct all the steps, essentially, that brought to an attack. So again, I will not be able to go into all the details of this, but to implement JSGraph, we leveraged the Chromium's own dev tools and expanded them by building our own inspector agent, which is essentially a module of dev tools that looks at all the JavaScript executions, DOM events, and so on and so forth to track everything related to JavaScript executions and interactions with the DOM. And this is just a detail in terms of how we implemented our inspector instrumentation hooks and sort of like a visualization of how the logs would look like. But like I said, the good thing was that once we had all these logs, we could use our graphing tool to analyze the logs and build sort of backward tracking graphs that would allow a forensic analyst to reconstruct an attack. For example, starting from a suspicious URL, the attacker could say, okay, show me what happened before this. Like, how did the browser get to navigating to this malicious URL? And essentially, that's what the graphing tool does, to do backward tracking and highlighting all the possible events that happened, JavaScript-related events, callbacks, and script executions, node insertions in the DOM, and so on and so forth. All right, sorry, I'm going a little bit fast because we are kind of running out of time. But another interesting thing was to say, okay, so we can do all of these. We can log all these details about how JavaScript executes, how it interacts with Blink, the rendering engine, and so on and so forth. And one thing that I forgot to mention is that not only we built this by instrumenting the code, but we were manually, but we were also able to automate some of the instrumentation process, essentially by writing code that would automatically instrument the interface between JavaScript, the JavaScript engine, V8, and the rendering engine, which is Blink. Like I mentioned at the beginning of the talk, there is a layer which is called the bindings that binds the JavaScript engine with the rendering engine. And actually, the browser inside has a compiler. So there is a compiler that takes the definition of the JavaScript interfaces, which are in a format which is called the web idle format. Anyway, it reads all these definitions and automatically compiles the binding code that binds together the JavaScript engine with the rendering engine. And we were able to essentially instrument the compiler for the bindings to automatically instrument all the bindings between V8 and Blink, which was actually quite a good result. Given the number of all the JavaScript APIs that one can use, of course, instrumenting them manually was an impossible task. In any case, the other nice thing about Chrome is that it has an infrastructure framework, which is called the trace events framework, essentially, or facilities, let's say, code that can be reused to measure events in a very, very precise way, like in terms of timing of events. And so I will not go into the details of all these results, but basically we were able to reuse Chrome's own tracking or tracing infrastructure to measure performance of the browser, to essentially evaluate what was the added time that would be introduced by JSGraph, right, by our own instrumentations. And so here, let's say we take page load as one example in terms of measuring performance of a head. And so we were able to show that if we take the time that it take measure the time at the when a load event, sorry, when a page starts being loaded by the browser, and when it ends loading, so with a load event that is fired by the browser, and we take this time and we look at, okay, how much overhead do we introduce here for in terms of JS graph compared to a standard browser execution. It turned out that the overhead was only between 3 and 8.2%, depending on the device and the specific situation, which was great. And that's for the sort of like 95% of the cases, essentially, of the pages that were loaded. And there are some outliers that where the page load is higher, but those are rare cases. And in terms of storage overhead, we actually demonstrated that JS Graph has even lower overhead in terms of storage than ChromePick, which was already already good. And we basically showed that the takeaway is that you could store all the logs produced by JS Graph during normal browsing, assuming that a user is browsing for eight hours straight a day. And this is an extrapolated result, but basically, if you assume that a user is browsing for so long every day for a year, the amount of logs that you'd store from JS Graph would be about 90 gigabytes per user, which in an enterprise environment, this would be quite affordable. Storage is cheap in a way. So, all right. So that's for the systems that we built to essentially enable audio logging, recording audio logs from inside the browser, from inside this new operating system that we don't think about it as such sometimes, but it is. And so besides enabling that, and so potentially allowing for very detailed forensic analysis of web attacks, it turned out that these systems that we built are extremely useful in other security contexts, which is measurements. So we had two recent papers, one in IMC 2019 and one in IMC 2020. Related to measuring, essentially discovering social engineering attacks on the web. So the first one was discovering ad-driven social engineering attack campaigns related to essentially sort of like standard ads on a page. So you might know that there's such a thing as malicious advertisements, unfortunately, which you can encounter depending on what sites what websites you visit, and so we built this system to basically try to visit as many pages that would potentially offer malicious advertisement as possible, and basically click on the malicious advertisement to follow the path, right? Follow the redirections and look at what pages would open, and essentially study what is the landing page, right? If we click on an advertisement from these shady websites, where does it take us? And then we had some, machine learning techniques for doing unsupervised learning, essentially clustering of the pages to find what are essentially social engineering attack campaigns and filtering out noise, which is potentially benign pages. And the good thing is that this information can be used, obviously, as you can imagine, to build social engineer, like real-time detection systems, right? That would potentially block social engineering attacks before the user actually sees these type of scary messages or scams of some sort. And I remember you worked on a paper about some type of scam, right, on the web. So the lottery, fake lottery, and so on and so forth. And so a follow-up on that was another similar work that though focused on a new type of attack, which is malicious advertisement that come from web push notifications. And so here, if you're not familiar with it, modern browsers essentially can offer the ability to for websites to send push notifications, right? Like you use on your phone, right? You're certainly familiar with push notifications on your phone, notifications from apps or notification from the system itself. Well, web applications can actually send you notifications as well. So even if you have that a website that you've previously visited and for which you allowed the site to send you notifications, even if you close the browser and well, it is on mobile, even if you close the tab, the page, and so on, you have, say, on desktop, you have the browser open, and you don't see whatever website you saw before, but that website can send you notifications if you agreed to do so previously. Now, these are used for legitimate purposes often, like sending news alerts or maybe reminders for whatever reason. Google Calendar uses this to send you reminders that there is an event coming up on your calendar and so on and so forth. Unfortunately, this can also be abused by attackers. And so we built a system that would crawl potentially malicious websites, automatically accept invitations to allow notifications from these websites, and then looking at what type of notifications they would send us, and then clicking on their notifications to see where they lead us, and then finding a lot of abuse, essentially. And in terms of ongoing work, so like I said, the talk was mostly about enabling attack reconstruction for forensic reasons, to enable a forensic investigation. But it turns out, like I showed you in the couple of slides, previous couple of slides, that those systems can actually be used for many other things. So we are working towards making good use of the systems that we already built to do more research on web security topics, especially social engineering attacks. We want to dig deeper on that and see if it is possible to actually do real-time detection of social engineering attacks using the instrumentations that we have already built for the browser. So in real time, you'd have this instrumentation that sends inputs or signals essentially to a detector that can be used as essentially features to recognize if there is a social engineering attack being rendered by the browser, not necessarily visually, but in terms of JavaScript execution events and so on. And another thing that we want to do is adapt what we have done for Android. I mean, we already have actually, the system that I talked about already work on Android as well. But we are thinking about, so there is Android Web View is a component essentially of Android that allows you for allows native apps to render web content essentially. And there are also ads, in-app ads that are rendered sometimes using WebView. And we would like to see if maybe we can explore that potentially malicious in-app ads as well, using the instrumentations that we'll build or that we will expand on. And then finally, we want to go back to the recorder replay topic that I discussed at the very beginning when I said, man, it was great to start there, but it was too ambitious probably. And in a way, we failed in the sense that we were not able to achieve all the goals we wanted. And one of them was deterministic recorder replay. It's very difficult. We are trying to narrow down the problem so that we don't do whole browser deterministic recorder replay, which seems to be too difficult. And we are trying to see if there is a way to adapt this to do deterministic replay of JavaScript applications in the browser. And I think that's all. And just an acknowledgement for the students who worked and led these papers and research projects that I discussed. And I guess with that, I'd be happy to take questions.